Hey guys, Professor Schupak here, back today with another video for all. Today, we're going to continue our discussion on dynamic programming, and we're going to use a very popular example known as the knapsack problem. So, how does this go? So, let's assume we have a bag, a knapsack, that is only capable of holding 5 pounds, and we have choices, item 1, 2, or 3, and we want to get as many items within possible range, with the 5 pounds we're allowed, to maximize the profit. So as we see here, item 1 weighs 2 pounds, but profits $3 for us. 2 weighs 4 pounds, but profits 5. 3 weighs 3 pounds and profits 6. And we want to know what's the best combination we can make while maintaining or being equal to 5 pounds in the bag and make as much money. So what do we put in the knapsack? And remember, we want to make money. If you recall in the previous video, there was a naive method that I mentioned where people go straight from step 1 to step 2, step 3. And although that might seem efficient, you could run into areas where once you stratify your data more and have a lot of different options, it might not be the best solution. And although you might make some money, it might not be the most. And because we like money, we want to make the most money. So again, we go through a recursive method where we start from the back. So this problem isn't a little visually appealing as the previous one. If you recall, where we did cities, we go to city 1, city 2, city 3, and we kind of branched it off. These are objects. So let's visualize a little bit better. So we have states and we have stages, right? States are any position you could be at any given moment. At any given moment, I could have 5 pounds left in my bag, 4, 3, 2, 1, 0. So we denote states as the capacity that our bag has left at any given moment. And we also need to define stages. Well, each stage, in the previous example, was city to city to city. We're not traveling from item to item, but after we choose to take or not take one item, we then move on to the next. So we're going to denote stages as the items. So stage 1 will denote item 1, 2 will denote item 2, etc. How do we go about this? So we have to start at the very end. That's how a recursive works, and that's how dynamic programming works. So we can make sure we have the most efficient option. So again, what states do we have at stage 3? Well, our bag could be completely empty. We have 5 pounds left. So what do? Well, we have 2 choices. We could take item 3 or not take item 3. Our choice is if we don't take item 3, we don't profit. And if we do take item 3, we get $6, so our best bet is to take it. If we have 4 pounds left, the same thing. If we have 3 pounds left, the same thing. It makes sense because if we're at the end and we have space for this object, we're going to take it because why not make more money if you can? It's free money in this case, essentially. Now, you see that F3 of 2, where 3, the number after the F, denotes the stage 3, and the number in parentheses denotes the weight that we have left. 2, 1, and 0 are all equal to 0. Why is that? Well, that's because in stage 3, we're dealing with item 3, and item 3 weighs 3 pounds. So if we don't have 3 pounds left in the bag, no matter what we want to do, we can't fit it, so we're not going to make any money because we will never be able to take it. So we see all our options at stage 3. Now we go back to stage 2. So on the left, we see again, this is the stage 3 results. So let's do the same thing for stage 2. If we have 5 pounds left, what are we doing? Well, we could take item 2 or not. So if we do take item 2, we have 5, which would be the profit we make off item 2, plus F3 of 1. Why 1? Well, we had 5 pounds, and we decided to take item 2, which weighed 4 pounds. That leaves us with 1 pound left. So what's our optimal option at the next stage? Knowing we only have 1 pound left, so it'll be 5 plus F3 of 1. And if you could see from before, we figured out F3 of 1 is 0 because we can't fit the next item, so that's 5. If we don't take item 2, we have 0 because we didn't get any profit from it. But we have 5 pound capacity, so F3 of 5, which would be 6, and that'll be the best bet. We do the same thing for all the others. So F2 of 4 would be the max. We take it 5 plus F3 of 0, which is 5. Or we don't take it 0 plus F3 of 4 is 6. And again, we get 6. Now, at F2 of 3, we know that we can't afford it. We can't take it because it weighs too much. It weighs 4 pounds. We only have 3. So we're not going to take it. So there's no choice. It's 0 plus the best bet at F3 of 3, which fortunately item 3 does weigh enough to fit in our bag, or light enough, and that'll be 6. And again, F2, F1, and F0 are all going to start with 0. We can't fit item 2 in our bag, and then we see what can we do? Can we fit item 3? So F2 of 2, we still can't fit item 2, and we can't fit item 3, so it's 0. F1 and F0, the same thing, so they all turn out to be 0, and that's stage 2. Now we're at the beginning. We're at stage 1. Now, the difference between stage 1 in these types of problems and the other stages is the fact that in the other stages, you could be at any point. because we made decisions on taking a bag and not taking a bag. And every time you make that decision, you have that non-added weight, so you didn't lose any weight or capacity left, or you did lose it. But at stage 1, we know that the bag is always going to have 5 pounds. We didn't take anything. We didn't start, and it's a 5-pound bag. So at every first stage, it's always going to be that weight you have. So we don't need to do 5, 4, 3, 2, 1. We only have 5. The other ones are not possible states in this example, which makes it easy because all we have to do is F1 of 5. So do we take object 1 or not? Well, object 1 gives us a profit of 3, and it weighs 2 pounds. So 3 plus F of 2. Or we don't take it, 0 plus F of 2. The 3 plus F of 2 gives us 9. If we don't take object 1, we have F of 2 of 5, which is 6. So 9 is better than 6. So the best profit we can make in this example is $9 by taking items 1 and 3. That is how you walk through a knapsack problem. I hope this helped you realize dynamic programming a little bit better. I understand that this example was pretty simple and you might have been able to do all this in your head, but that's because we only had 3 numbers. Imagine if you were given the same problem by your boss or a project or whoever might ask you, and they give you 1,000 objects to choose from. Not something so simple to do in your head. So as you can see, dynamic programming is a very important concept and topic because when we do get larger numbers and larger data, we have to understand the process of calculating this and how we go about solving it when we get to terms and sample sizes that are way too large for us to write down, think of, or compute on our own, and that's where we go to computers. Thank you guys for watching this video. I hope this helped you understand dynamic programming a bit better and at least taught you the knapsack problem. I hope you guys like, comment, subscribe, share it with a friend if you thought it was helpful, and I'll see you guys in the next video.